Hello, I'm Riley Spawn from Columbia University, and today I'll be talking about Pyramid. And Pyramid is our system for enhancing selectivity in big data protection. And this is a broad vision about being selective in how you use data and with the purpose of trying to reduce that data's exposure. So, let me see. So, companies have a collect everything mentality. They view data as having limitless value, and as a result, they will collect as much data as possible. This mentality raises substantial risks both in the uses of that data and in how that data is managed. So compounding this collect everything mentality is the troubling practice of data lakes, where a company pools all of the data that it collects across many services into one big data repository and gives wide access to that repository within a company. So let's take a simple example. So let's take a simple example that we're calling MediaCo. This is a media conglomerate that owns hundreds of websites across different verticals. So, and each of those websites collects a stream of user activity, that user on each site, and then the data from all of those sites is integrated and pooled together into one common data lake. And then teams across the organization will all get access to that data lake to perform different activities like article recommendation, ad targeting, etc. So this type of infrastructure is common. Microsoft Azure has a data lake product that's ready to deploy, and Amazon has documentation on how to build a data lake using their existing offerings. The problem with this type of wide access infrastructure is that it raises substantial risks. So the problem is that it's not amenable to isolation, control, or auditing. If a single team is compromised in the organization, then that compromises this entire lake of data. The data that the organizations value so much and the fashion in which that data is managed make it very valuable to attackers. So in our research, we're asking a question. And that question is, can companies be more selective about what data is collected and how they give access to that data? So we hypothesize that not all of the data that's collected is needed or even used. If one can distinguish between data that is needed now or will be needed in the future from the data that is collected just in case, then one can protect the latter data in a much stronger fashion, like storing it offline and auditing all of the accesses to it. So in our work, we are building what we're calling selective data systems. And these systems will, by design, differentiate between data that is needed, which is used and widely accessible, the top of the pyramid, from the data that is unneeded and unused and will be tightly protected, the larger base of the pyramid. So we define selective data systems by 3 goals. So the first goal is that we must minimize the exposure of the in-use data in size, time span, and sensitivity. Second is that we must avoid accessing unused data for current and evolving workloads. And third, we must accomplish these 2 goals without impacting accuracy, performance, or other functional requirements of the system. So in this work, we specifically investigate how do you achieve selectivity in machine learning. So in traditional systems, the approach to determining what data is in use is to look at the working set and access patterns. These approaches assume that the working sets will be relatively small and stable over time. However, machine learning workloads have different characteristics, like when retraining a model, you will likely touch a large amount of data a small number of times. And in these cases, the access patterns will give you very little insight into what data is most important. So what we're trying to do is to look at training set minimization techniques. These techniques attempt to find subsets of training data that are most useful to a learning task, or to transform that data into a form that allows for more efficient learning. So in our specific system, we investigate count featurization, which is a particular type of training set minimization, and attempt to retrofit it for protection in our system, Pyramid. So Pyramid is the first selective data system. It retrofits that particular training set minimization technique for protection. And the way that it generally works is that we keep on hand a small amount of recent raw data, and then we summarize the past using differentially private count tables. And then when we go to train machine learning models, we will combine the raw data with data from the count tables and use that and then feed that into the models for training. And in doing this, we can reduce exposure by 2 orders of magnitude with moderate performance degradation. So now that I've introduced Pyramid and its basic approach, I'm going to explain the Pyramid's design for retrofitting count featurization for protection, and then I'll walk through some evaluations showing that it can realistically leverage count featurization for data minimization and selectivity. So Pyramid's architecture looks something like this. It acts as an intermediary between machine learning models and all of the data that they use for training and retraining. It leverages count featurization and differential privacy. It keeps count tables of history which are in the form of like a contingency table, and then a small amount of recent raw data. And then we'd expect that the majority of the company's data would be stored offline in some kind of a cold data store that's rarely accessed. So Pyramid operates on streams of observations. So when an new observation arrives, this would be a observation that consists of a feature vector and a label. Pyramid needs to keep the count tables up to date with recent raw data, so it uses that so the count tables are updated. We write the observation into the recent raw data store, or the recent raw data, and then update the cold raw data store. So how do we use these count tables for featurization? So I'll walk through this with an example. In this example, we want to build a binary classifier that predicts if a user will click on an ad based on three features: the ad ID, the user ID, and the page ID. And we keep a count table for each of these features. The count tables have 1 column for each label and 1 row for each of the feature values. And in this case, all of the count tables are initialized to 0 because they have not been populated with any data. So as observations arrive, we increment the appropriate cells and do this for each observation that arrives until we have populated the count tables with data for thousands of observations. And then when we need to featurize an observation, we take the observation, calculate the conditional probability of a click given each of the features, and then replace those features with the conditional probabilities. And we use that directly as a feature vector to be fed into the machine learning model. So many features like the IDs shown here have cardinalities that can reach into the millions. So count featurization can permit more efficient learning, allowing us to use drastically smaller training sets and thereby reducing the exposure of the data. So we need to use count featurization to featurize data when retraining models and when serving prediction requests. So a prediction request will arrive at one of the models, and that prediction request will consist of a raw feature vector. That feature vector will be passed from the model or model server into Pyramid. Pyramid will use the count tables to count featurize that feature vector, and then that feature vector is passed back up to the model to execute the prediction. So the protections that Pyramid provides are best illustrated as a timeline. So Pyramid keeps 2 sliding windows of data. The first sliding window we call the hot window, and the hot window consists of the recent raw data that will be used for retraining. And we expect that the size of this window would be days or weeks of time. So the second window is the retention window, and the retention window is much longer, and the observations that fall into it are used to populate the count tables. And we expect that the retention window would be on the order of months or a year. And then the data that falls out of these two would be stored offline and presumably inaccessible. So in the event of an attack, the adversary will gain access to the small amount of recent raw data, and then the adversary will also gain access to any new observations that arrive before the attack is mitigated. And finally, the adversary will also be able to see the values of the count table, but we have not kept the observations that we use to create the count table around. So the count tables themselves are differentially private, so that should provide some privacy for the observations that were used for population. So for these protections to hold, Pyramid makes 3 assumptions that must be met. First is that state is not managed out of band. This means that an analyst or developer cannot copy data from the hot window or count tables locally. Pyramid must do all of the data management. And then we assume that all of the models are retrained when Pyramid requests it. This is because that the models will contain information about the hot window and count tables on which they were trained. So these must be kept in step as they slide. And finally, state from the previous models should not persist. This follows from the previous assumption and means that the current models must only reflect data in the current hot window and the current count tables. So, as I stated previously, we use differential privacy in conjunction with these count tables. And the general idea for differential privacy is that you randomize outputs from functions are randomized to protect privacy. And the amount of randomization is based on a privacy budget epsilon. And the smaller the epsilon, the smaller the privacy budget, and the more randomization. And this privacy budget epsilon can be shared among a number of queries. So differential privacy has two nice characteristics. That the first is that it is resilient to auxiliary information, and the second is that it is resilient to post-processing. So this means that after we have the differentially private count table, we can count featurize data and use it to train any model, and the observations used to populate the count table would still be private. So we leverage differential privacy by rather than initializing the count tables with 0, we initialize them with draws from a Laplacian distribution. And that privacy budget is shared among all of the features. So the more features that a model has, the more randomization the larger the Laplacian distribution would be. So the differential privacy, we combine it with count featurization in building these count tables. And the structure of the count tables looks something like this. So the count tables that we've shown in previous slides are actually made up of many smaller count tables. And we split the retention window into many smaller discrete windows of time. In this case, we keep a count window for each day. And in order to compute the counts that are needed for featurization, we just sum the count tables together. And when the retention window slides and we initialize a new table, the cells of the count table are initialized with values from the appropriate Laplacian distribution. They are incremented with new observations, and then that window is added to the summation. And then whenever a day falls out of the retention window, we simply remove that window from the summation. So many challenges arose when trying to combine count featurization with differential privacy. I don't have time to go into them here, but all of the challenges are detailed in our paper, and all of the solutions, we have evaluations for all of these solutions. So now that I've talked through the approaches that underlie Pyramid, I'll go into some of the evaluation showing that we can train models on smaller amounts of recent data, reducing the exposure, and have those models perform competitively with models trained on the full data set. So today, I'm going to talk about the evaluation on two data sets. The first one is a data set released by the ad targeting firm Criteo for a Kaggle competition. And the goal of this data set is to estimate the probability that a user will click on an ad given 39 features. And the second data set that we look at is the Movie Lens data set released by the University of Minnesota. And this data set is a series of movie ratings, users rating movies, and also consists of a number of demographics about the users and characteristics of the movies. So all of the figures that I'll show have this same structure. The x-axis shows the fraction of the raw data that was used for training, and the y-axis shows the performance normalized to the model trained on the full raw data set. This makes it easy to compare. So the blue line that's up there now shows the performance of a 35-node single-layer neural network trained on increasing fractions of the Criteo data set. And you can see as we add data, the performance continues to improve. And note that the x-axis is in log scale. So the orange line that I've added is a model trained on increasing fractions of count featurized data. And the models trained on count featurized data tend to converge much faster to close to their maximum performance, much faster than the raw models. And in this case, it converges faster, but we have a 2.6% loss in performance. The green line that I've just added shows the performance of count featurized data, but with a differentially private count table with epsilon equals 1. And in this case, that costs another 0.6% in performance. But what this means, overall what this means is that training on just 0.4% of the data in this instance leads to only a 3.1% loss of accuracy. So we could potentially reduce the overall exposure by 2 orders of magnitude with a 3.1% performance hit. And we see similar results from the movie lens data set, where we can expose just 0.8% of the data and for just under a 5.5% loss in accuracy. So using count featurization, we could potentially reduce the exposure of the amount of data that we need to expose when training models by 2 orders of magnitude. So today I've talked about how aggressive data collection and wide access practices increase data exposure risks for companies and organizations. And I've introduced selective data systems that minimize in-use data and cleanly separate it from the unused data, and propose training set minimization as a new way to think about selectivity in the context of ML workloads. And finally, I talked about Pyramid, which was our first selective data system that retrofits count featurization for protection using differential privacy, and shown that it's possible to reduce data exposure by 2 orders of magnitude. So I'll leave you on this future work slide and take questions.
Thank you. And we can also welcome the other first author to help Riley, Matthias step up to the stage. Go ahead.
Ben Fuller, University of Connecticut.
Yes.
If you're using a count featurized system, why do you need to keep the hot data in your local data store at all? Why can't you just get rid of it and put it in cold storage?
Because we have the small amount of recent raw data. We actually I walked through an example of how we perform the count featurization. So we actually transform that small amount of raw data and use that to train the model. So we need it for model training.
So aren't you worried that you've increased the privacy risk for people while they're involved in that hot data set?
Yes, it does. I mean, it shouldn't increase the privacy risk any more than just training on the raw data. Our hope is that just exposing that much smaller fraction of the data would have a benefit for protection.
But the model is more dependent on that data now.
That's possible, yes.
Thank you.
Hi, Ellie Cadell, Software Engineering Institute. One thing which I noticed, so if you're doing these count tables, you had a slide which showed conditional probabilities.
Yes.
I assume those are being stored at the time of the counts?
So those are stored, they're stored online, and they're stored and updated online as you receive new labeled observations.
So if you wanted to calculate a new conditional probability based on some new data,
yes,
data
if you
features.
needed, so if you needed to do that, that would be a evolution in your workload. So if you want to start predicting something new, so rather than predicting if someone would click, you want to start predicting retention time, you would have to go back to the raw data, to the cold store, and compute all new count tables.
Thank you.
Yes.
Thanks. John Criswell, University of Rochester. I'm a little confused about your attack model. Are you trying to protect just against queries to the database, or just attacking from, say, more low-level attacks? Because it's not clear to me that moving data into offline cold storage is actually going to protect things, unless it's just not accessible to queries.
The idea is that it would be much less accessible to queries because the idea is that you would make accessing that data very exceptional. So make it exceptional so that when data is needed to be accessed, you would be able to do some kind of strong auditing or access control on that.
Okay, so something like shipping the data off to a remote server that just doesn't let you, read it once you send it off.
Yes,
correct?
yes. And then in your kind of, what you keep online is the small amount of recent data and the count tables. So,
okay, thank you.
Let's thank all speakers of the session.
so.